Welcome back, folks. We're still looking at mesh analysis, and we're trying to find the mesh currents. And we're analyzing circuits that have current supplies. The last problem that we looked at in the last video had a current supply, and that current supply had one mesh current flowing through it. And it's the simpler of the two cases. We just trade a KVL for a KCL, and we're done. Okay, we write the rest of it the same way. Here's the more complicated, slightly more complicated, you're going to be fine, I promise you, instance where we have a current supply in a mesh analysis problem. Look at this current supply, and you'll see that we have two mesh currents that touch that. Okay. Once again, the problem's annotated already for you. It's coming out of my lecture notes that I use when I'm in front of the classroom. And I labeled them both clockwise, I1 and I2. I went through the same thing, right? We're labeling the same thing. I labeled polarities the same way that I usually do. So I1, every passive component, positive, negative, and then these two are active components. Okay, working our way around here, I did the same thing. That's an active component. Here's a passive, positive, negative, positive, negative, positive, negative. All right. When we write KVLs, we're going to write them a little different this time, but when we write KVLs, we're going to use those polarities. We're still going to use those polarities. Okay, so this case has a special name, and if you go read the textbook, the recommended text for the class, or really any circuits textbook, is going to have something along these lines in it. Where is my pen? My pen isn't working. Stand by. Much better. Okay. Any circuits textbook is going to have these special cases in it, and depending on the textbook, it's either going to be called a super mesh, okay, or a super loop. I've always wanted to wear a cape. This might be my chance. I've always wanted to wear a cape and like a Superman shirt when I'm teaching this one, but I don't think I have a Superman shirt, and the only cape I have is my kid's, so it might not really fit me. And hopefully it's not green. I think it's red. Anyhow, maybe for the nodal analysis one. When we have something super going on there too. Okay, super mesh or super loop. So we can define these. A mesh analysis problem has a super loop if a current supply, IS in this case, if a current supply has two mesh currents flowing through it, or touching it, right? Flowing through it. We've got to treat this one differently. And here's why. I have two unknowns. I still have two unknowns, I1 and I2. I got to go find those. And according to my plan, if I see a current supply, and there is one, right? 6 amps right there. If I see a current supply, I'm going to write 1 KCL. And if I have two unknowns, I need one more equation, so I'm going to write 1 KVL to make up the difference. And that's going to cover my two unknowns. Okay, that's my plan. I made a little plan. Those are the types of equations I'm going to write. The KCL, it's not a big deal. We know how to write those KCLs. Right? This current right here is 6 amps. We know that because of that. Okay, well, so how do we express that current? Does I1 touch it? Let me get a good pen color here. And we're going to write the KCL for the super loop. Okay, so does I1 touch it? Yes, it does. Does it go in the same or the opposite direction? Well, if I go clockwise around here, it looks like it's going down when the positive direction is labeled as up. So it goes in the opposite direction. It's negative. Does the... Why did I pick this color when I'm really writing it for both colors? It's a thing, because I didn't think. Does I2 touch the current supply? Yes, it does. And it goes in the same direction. Okay? And that's equal to IS, which we know is 6 amps. So that's our equation. It's already done. Look at that. A bunch of constants and our unknown mesh currents. And we are good to plug that one in. Now, here's my problem. I need to avoid this current supply because I don't know its resistance. So I can't rewrite the KVL in terms of the unknown mesh currents. So I can't write the KVL for I1 because the current supply is included in that mesh. And I have the same problem when I write the KVL for I2. That's still included in the mesh. So I have to avoid it altogether. And the way that I avoid it is I take the two meshes that flow through, the two mesh currents that flow through that current supply, and I combine them. It's like bubbles. Like if you, I guess I've been playing bubbles too much in the summer here. You blow bubbles, they stick together, and then they form one big one, right? So these are two bubbles that are stuck together. And then together, they form one loop. Okay? And it's super because it's bigger than either of the two that make it up. Okay? That's your super loop that I just drew in green. And that's the path we're going to follow when we write the KVL. Okay, so let's start to write that KVL. I'm going to try to squeeze it in down here for starters at the very least. So this is the KVL for the super loop, super KVL, super KVL super, as long as you know what you're doing there. So we're writing a KVL. I'm going to start here. I go up across VS. Okay, I go down across the 6 ohm, which I believe is labeled R1. Okay, I go down across R3, which is that 10 ohm in the top right, and I go down across R4. Okay, so I went up, down, down, and down, and I'm back to where I started, so that's equal to 0. R2 doesn't come into it anywhere. Do you see R2 anywhere in here? The value of R2 doesn't affect the circuit. It doesn't. Okay. And let's see. Now we've got to do some substitution here, and we can say 20 volts. The minus comes down. VR1, getting a little big here. Using that polarity, does I1 touch R1? Yes, it does. And it flows in the positive direction according to the passive sign convention. Okay, so this is going to be I1. Does I2 touch it? No, it doesn't. So then I just multiply by R1. That one's done. Bring this negative sign down. We're looking at this drop. Does I1 touch that resistor? Nope. Does I2 touch that resistor? Yep. And it flows in the positive direction according to the passive sign convention. So it's just going to be I2 R3. Okay. Last one, the minus sign comes down. Does I1 touch R4? Nope. Does I2? Yep. And does it flow in the same or opposite direction? It flows in the same direction as the positive current according to the passive sign convention. So this is going to be I2 times R4, and then we bring down the 0. So we just have to rearrange some things and get it in the form we want it to, and maybe plug in some more values as well. So let's look at our I1 terms, and that's it. So it's going to be negative R1 I1, swapping the factors around there, plus minus R3 minus R4 in front of I2. The 20 moves over to the right-hand side by subtracting it from both sides. So we have negative 20. Oh, not yet. I want to plug in values. I got excited. Sorry. We got to plug in values. R1, check the image, but you'll find that it's 6 ohms. I'm not going to scroll up here. Okay, negative 6 ohms. And then negative R3 and R4, 10 and 4. So we're going to have negative 14 I2. And on the right-hand side is still negative 20. There we go. That is ready for my system of equations. So let's scroll down a little and let's set it up so that you're ready to solve it using whatever tool you choose. Okay, we'll go white for this. It's going to be 2 by 2 because there's still only 2 unknowns. I look at this equation up here and I say negative 1 is the coefficient of I1, positive 1 is the coefficient of I2. I'm going to put that in a matrix and I'm going to invert that matrix and multiply it by a vector of the right hand side. So that's positive 6. And if I do this operation, I'm going to get a vector of my unknowns I1 and I2. Okay, let's not draw that one yet. Let's get the second equation in there. The coefficient of I1 is negative 6. The coefficient of I2 is negative 14. And the right-hand side is negative 20. Okay, so pause the video, do whatever you need to do to solve that system of equations. I want you to practice it, but I also want you to have the answer that I get, hopefully the right answer, right? So that you know whether you've gotten the right answer out of your tool, whatever you're using. Okay, so negative 1, 1, 6, negative 14, and negative 20. And from that, this feels familiar, negative 3.2, almost as if I've been using this example for years and years and years. Okay, negative 3.2 amps and 2.8 amps. Okay, and then if I go check my notes on top of it, that gives me a little more confidence that I at least calculated it the same way twice. And I did get those values. All right, so this is our first super loop. We have to be able to recognize when it's part of the problem because it changes what we do a little bit. One of our KVLs ends up going around 2 meshes to avoid the current supply. We don't want to write a KVL across a current supply most of the time. We're going to find an example where we actually do want to do that. Okay, but finding the mesh currents, we want to avoid it. Finding the mesh currents, we avoid it altogether. All right, where do we go from here? I think we should do another super mesh or super loop problem. Like I said, the textbooks use those interchangeably. And we'll make it a little bigger so that you get a little more comfortable with this. Okay, so stay tuned and good luck.